She's been very involved in the IEEE Robotics and Automation Society. She's on the organizing committee for this conference and is currently the vice president of technical activities, member activities, sorry. You can tell I don't have the bio in the program. She's previously served as an NSF program director in the area of robotics and is the site director for an NSF Industry University Cooperative Research Center in the area of robotics and sensors for human assistance. So she's going to talk to us today about autonomous continuum manipulation. So let's welcome Professor Xiao.
Thank you, Don. And I have to add that I got my PhD from the University of Michigan, and it's nice to see Michigan now is booming with a big robotics program again. So, thank you for coming to my session. I'd like to talk about autonomous continuum manipulation. So continuum manipulators are inspired by interbrick structures found in nature, such as octopus tentacle or elephant trunk. Because it's continuously deformable and can be very compliant upon contact with objects. So this type of manipulators are very suitable for whole arm manipulation in very cluttered environments. There are a number of excellent review papers on the literature of continuum manipulation, starting from Hirose's seminal work in 1993 and all the way to the recent work by Xiao, which is to appear in the special session on continuum robots and manipulation of the advanced robotics in July. So the history of continuum manipulators can be traced back to, the design by Anderson and Horn and Hirose on tendon-driven arms. And as Xiao's work pointed out, the hyper-redundant manipulators like snake robots shown here actually approximate a continuous backbone structure. So since the 1990s, there are a lot more development in the hardware and kinematics, dynamics, and control of continuum manipulators. So in addition to tendon-driven design, there are other types of designs, such as the locally actuated design, as represented by the pneumatically driven OCT-arm from Ian Walker's group. Also, there are concentric tube designs for medical applications. So of all of these different types of continuum manipulators, they share some common characteristics. Each manipulator consists of serially and tangentially connected sections. And each section has a uniform curvature at every intact configuration, that is, if it's not deformed by contacting with objects. So the section can be considered circular, and each section may change its length, orientation, or curvature, but depending on different designs, some of these parameters may be constant. So we consider a manipulator model of an N-section manipulator try to capture all these common characteristics. And each section has 3 degrees of freedom described by 3 variables: section length, section curvature, and orientation angle. Each of these variables, so they may change values. And each section, as I mentioned, is circular if it's intact and defines a section plane. So I'm going to talk a little bit about the existence of whole arm grasping configurations for autonomous manipulation and fast collision checking for also the practical purpose of motion planning and some different manipulation algorithms. So we've studied the existence of grasping configurations for a 3-section continuum manipulator inspired by the OCT-arm at Clemson University. So each, if a grasping pose exists, we try to find all the grasping configurations. What we found is if the tip section is on an object circle, such as this green one is on some object bounding circle, then there are multiple regions, connected regions of solutions. Each region, of course, has infinite number of solutions, but if we add other kinematic constraints on reachability of the objects and so on, the solutions may be finite in some cases. Otherwise, if the more than one section is curving around an object, then we have finite solutions. So we find those solutions by solving intersection constraints, such as for adjacent two sections, their circles have to be tangential. We also considered this challenging problem of collision detection. Well, it's challenging because of some unique things about the continuum manipulators. A continuum robot can continuously deform into different concave shapes, and each newly deformed shape requires an updated mesh, which can be time-consuming because it requires the mapping from high-dimensional configuration space to the Cartesian space. As in shown in this example, we have a 3-section manipulator, then there are 9 degrees of freedom. And also, a concave shape requires a much finer mesh to represent than a convex shape. I'm talking about mesh because in the conventional collision detection algorithms, usually objects are represented as polygonal meshes. So if we use a common mesh-based collision checking approach, continuum manipulators can be quite expensive as the manipulator changes configurations. So we considered using the parametric model of the manipulator to directly check collision against any object mesh analytically. We consider for a polygon of an object mesh, first, if it intersects with the cross or section plane of a particular section, then the problem is converted into just a 2D checking between a line segment and a circular segment. Otherwise, we consider the distance from the polygon to the section or the section of the manipulator by a combination of basic distance computation, computations such as point to plane or point to line segment and point to circular segment computations. So this is quite fast, and we don't have to build and update mesh models for the manipulator in different configurations, and uses less than 20% of the time of a common mesh-mesh collision checking algorithms. So for each configuration, a few milliseconds, well below 10 milliseconds, is enough to do collision checking, even for a fairly complicated case involving complicated objects. So this is just a very practical solution to facilitate a lot of our later algorithms. And this is an experiment conducted with the Clemson arm robot. This is a collaboration with Ian Walker's group. So we have an overhead connect sensor to sense the robot pose and also the object. And then the object grasping configuration and motion to reach the grasping configuration is computed and executed autonomously. So we leave the object to show that the force closure grasp is obtained. And here's another example. And we put an obstacle in the way. So the robot will have to avoid this obstacle, a brick-like obstacle, in order to wrap around the target object. This is 1.5 times sped up, so it's not that bad. But because the robot is operating in an open loop in those experiments. Okay, just one more example of a different obstacle and a different object to be grasped. So I think I can further speed this. Okay, so next we considered what if we don't know any bounding circle of the sort for object. They want to still achieve force closure grasping through progressively producing a grasping configuration. So this shows an example algorithm. So initially we computed the arm to be in contact with this object, and then we curl each section from that point on towards the tip of the arm one by one, and to produce a spiral type of a grasping, avoiding self-collision. And we do a force closure check to make sure that the final configuration is stable. And otherwise, we readjust the parameters for spiral. So this shows an experiment. Again, using the octarm manipulator. So we can see that force closure grasping can be achieved. However, if we put an obstacle in the way, this kind of open wrapping of the algorithm is not working. So the robot will hit the obstacle. And another failure case. So that inspires us to consider grasping in cluttered space, using minimum maneuver space to achieve a grasping effect. So from an initial configuration, we move all the arm sections simultaneously in small steps towards the respective targets for the tip of each section, while avoiding collision, and eventually achieve force closure grasp. So for each arm section, we use different strategies to reach its target vertex, from the very greedy strategy of trying to reach the furthest reachable and visible vertex on the cross-section of this arm section of the object, to the much more conservative, always try to reach the nearest visible, and some random vertex in the middle, in between. So we can see some interesting time and space trade-off in this case. We're comparing three strategies now. The first strategy is the most greedy strategy. It can operate much faster, but uses more maneuver space. The second strategy is the more conservative strategy, always try to reach the nearest vertex, but it uses the smallest amount of space, but also much slower. As you can see, the first strategy already accomplishes a force closure grasp, and the second one is still working, and the third strategy has a performance in between the first and the second. Just an interesting thing about space-time trade-off here. Okay, so finally, the second strategy will also stop, but uses very small space for maneuvering. And we try to find the so-called feasible configurations by repairing collided configurations. So if a collision happens between the arm and some obstacles, then we have this efficient heuristic to repair by curling the collided section and shrinking the previous section. If the collision happens with the target object, then we repair by flattening the collided section and extending the previous section. The strategy turns out to be very efficient in generating feasible configurations. And again, here's the real experiment. If you remember, in this case, the previous strategy of opening the arm and wrapping around the object doesn't work. But this strategy now works quite well in avoiding the obstacles. Okay, this is a close-up. Oh, didn't, sorry. This is a close-up for the same operation from different viewing angle, so you can see a little bit more clearly. Next, we also considered task constraint manipulation, inspired by the applications of inspecting difficult structures in cluttered environments or hazardous environments, such as in a nuclear power plant. Here is a simulation inspired by the real situation of inspecting this pipe with the arrow point to. And in this kind of situation, a continuum arm works better than an articulated arm. So we're quite interested in this kind of task constraint manipulation. The constraint is on the tip of the manipulator. If we have an inspection device on the tip, then we want to make sure that a certain orientation and position of the tip should follow. So here's an example with the position constraint to be of always maintaining constant distance between the structure inspected and the tip. The tip of the position always maintains a constant distance between the surface it inspects and itself. So this is like a raster style scanning. To search for feasible configurations here, one challenge is to deal with the redundancy of the arm. In this case, we have a 3-section manipulator, and with a mobile base, that's 12 degrees of freedom. So even if the tip position is constrained to be on some fixed curve, there are still many redundant degrees of freedom. So the issue is how to search for feasible solutions in this kind of high-dimensional space. So our approach is to use the shape of the arm as a guidance, in the workspace as guidance. We start from the most constrained shape of the arm, which have all sections form one big circle, and gradually relax the shape constraints to, if necessary, to find suitable solutions. So we start from a very limited subspace of configuration space to find a feasible shape and pose of the robot. And if necessary, we gradually increase the search space. So this shows, this video is pretty long, so I'm going to speed up, but it shows that you can cover the whole structure. Okay, so how about orientation? In this video, we show the tip, orientation of the tip is constrained to be always tangent to the surface it examines. So imagine we have a inspection device at the tip of this kind of robot. And this now shows, again, a different orientation constraint with the tip being orthogonal to the surface, while maintaining also constant distance from the surface. So our algorithm is actually quite general. It can deal with any kind of orientation constraints on the tip and the position constraint on the tip. And also, it applies to mesh representation or point cloud objects. So pretty general object and obstacle representations too. And as you can see, the space is fairly narrow, so we can deal with this kind of cluttered environment. Now this is, again, one more example showing a different object and different kind of inspection, with the orientation constraint being 45 degrees. So the tip of the robot, its extending axis should be 45 degrees from the surface of the inspection. And also the base of the robot in this example is fixed. So again, we can speed up this a little bit, but you can see it's fairly narrow space. Okay, now a real experiment to have the tip of the robot following a straight line up and down for inspection purpose. So we don't have any speed up here, it's just a real speed. Next, we considered progressive grasping. By progressive grasping, we mean we gradually generate a grasping configuration in unknown structure based on sensing. So here shows an example. If we have a milk can to be grasped, and on the tip of the robot, we have a sensor, a RGBD sensor, for example, that can sense the gap between the target object and the surrounding structure or obstacles. So as we gain more information of the surrounding objects, we gradually generate a grasping configuration like this one. But the most important thing is we have to decide if a solution does not exist, we're not going to force the robot on, we're going to retrieve the robot. And this one shows a case when the solution doesn't exist at this point, when the robot is going to wrap around this part of the object, the gap is too narrow. And in this case, the gap is wide enough for the same area to be grasped, but in order to make this robot wrap around this object, this space, the top space is too narrow. So we have to consider a concatenation of these so-called gap constraints in simultaneously as we started discovering the structure and object to decide if a solution exists. If a solution exists, we can always find it. Okay, so here's a simulation to show that. All the objects are in point cloud from the RGBD sensing. Of course, this shows a view. We put the point clouds in the simulation environment and run the simulated robot, in this case, just to show the real-time processing for grasping. And this is the example when a solution cannot be found in the middle of the grasping, as the robot explores the environment and tries to grasp the object. Finally, another example. I'm speeding up a little bit. And again, there's no solution. So to sum up, I've talked about some of the work we've done on autonomous continuum manipulation. But certainly, this is a very interesting area with a lot more work need to be done, especially real-time manipulation in cluttered unknown environments. I've shown a combination of real sensing data and simulation, but we need to do it in real experiments. And real-time manipulation of unknown objects. How about the target object is size? Everything is not known. We have to detect it on the fly, or inspection with more constraints, task constraints, and manipulation of deformable objects in contact space. So the manipulator now is not circular anymore because of the deformation, and that requires shape sensing. And in this morning, I've heard a talk from Johns Hopkins University, a very nice talk about optical shape sensors to sense the optical fiber sensor to sense the shape of the robot. So this kind of manipulation is very needed for medical applications. So I'm going to finish my talk by thank the students and collaborators. My student, Jing, a PhD student, is a major researcher behind all this work. And another student, Zhou Teng, who is actually sitting here. Also, Ian and Puva from Clemson University. As you can see, we use the OctArm to do a lot of experiments, and their work has been a major inspiration. And the funding from National Science Foundation and also the Industry University Collaborative Research Center under NSF from our industry partner, Electric Power Research Institute. So John Lindbergh and Robert Greasy of EPRI pointed out the inspection problems, and we've been having fun working on those problems. So that's it for my talk. Thank you for attending.
Thank you very much, Jing. We have time for some questions.
So how is the cost of these continuous manipulators continuum manipulators compared with the normal actuated manipulators, and when do you think they will be comparable or something where we can actually start using them in the industry?
This is a great question for Ian, actually. The cost of this kind of manipulators.
Okay, any other questions? Yes.
On a number of your algorithms, you talked about checking whether it makes contact and then continuing to grasp based on that contact. What types of sensors are you using to see whether you made contact?
Oh, you mean the force closure kind of grasp?
Yeah.
We actually don't have a sensor on the arm itself, so we just take full advantage of the compliance of the arm. We make the arm just consider the object to be smaller than it is. So it's just like that.
Okay.
And another question over here.
Okay, thank you. Two small questions. One is related to the speed in the videos. What's the speed limitation? It's the real-time calculation? Yeah, some of the videos were sped up, as you said. So what's the limitation on the speed? Is it due to the time needed for the real-time calculation, or?
All the videos except for one is the original speed.
Yes, but what's then the limit for the speed? What's the limit for the speed?
What's the limit for the speed?
Yes. Can you go faster if you would like to go faster?
Oh, we can go. The algorithm is very fast. It's just we deliberately make the robot execute in a slower speed because the robot is open loop. There's no closed loop control for the robot.
Yeah.
But the algorithm, all the simulation, see the speed is what you see is what you get.
Okay.
It's really real time. And for one experiment, the very initial experiment I showed with the grasping, we deliberately make the robot move slower for going up to the to make sure that things are safe. But
Okay.
even that, the speed up is only 1.5 times.
Okay. So the other question that I had is, I did a similar application in a nuclear power plant with a more conventional robot to do the inspection, ultrasonic inspection. But typically the sensor head is quite heavy. So I was wondering if these continuum robots can carry a reasonable tool of reasonable weight at the end, at the tip.
That's a very good question. Actually, I don't know the answer right now because we're interested in this
Okay, I think it's time for the coffee break. So I'd like to thank you all for, did you want to make a last comment? Okay, we can ask more questions during the coffee break, but thank you all for attending, and let's thank Professor Xiao once again.